In the late 17th century, scientists believed they had discovered the essence of fire itself, a mysterious substance called phlogiston. For nearly a century, this theory dominated our understanding of combustion, breathing, and metallurgy. Today, we're exploring how this elegant but ultimately flawed theory rose to prominence and eventually collapsed, giving birth to modern chemistry in one of history's greatest scientific revolutions. Our story begins in 1667, Germany, where alchemist Johann Joachim Becher proposed a revolutionary theory to explain why things burn. Becher suggested that all flammable objects contained a mysterious fire-like element he called terra pinguis, or fatty earth. When objects burned, this substance was released into the air, explaining the flames we see during combustion. This concept wasn't just a random guess. It was an attempt to systematically explain natural phenomena at a time when alchemy was gradually giving way to more rigorous chemical investigations. In 1703, Georg Ernst Stahl at the University of Halle refined this concept, renaming it phlogiston from the Greek word for burning. Stahl wasn't merely rebranding an idea, he was attempting something truly ambitious, creating a comprehensive framework that could explain all chemical transformations through a single unifying principle. This represented a crucial step toward modern scientific thinking, moving away from treating each phenomenon as unique and instead seeking universal explanations. For nearly a century, phlogiston theory dominated scientific thinking about chemistry. According to this theory, when materials burned, they released phlogiston into the air. The more completely something burned, the richer it was in phlogiston. Metals were considered compounds of calx, what we now know as metal oxides, and phlogiston. When metals were heated, they released phlogiston, leaving behind the calx, which explained why metals gained a powdery appearance after being heated. The theory had an elegant internal logic that unified diverse phenomena. When wood burned, it released phlogiston until depleted, leaving behind ash. When animals breathed, they absorbed phlogiston from the air and released it through exhalation, which explained why animals couldn't survive in closed containers. The air became saturated with phlogiston. The theory also explained why burning required air. Air had a limited capacity to absorb phlogiston, which is why fires went out in enclosed spaces. This aligned perfectly with everyday observations and provided a satisfying explanation for combustion processes. Some physicians even extended the theory to human health, suggesting that excess phlogiston in the body caused fevers and inflammation, while its deficiency might cause other ailments. Despite its widespread acceptance, troubling contradictions began to emerge in the phlogiston theory. The most significant problem was that some metals, like magnesium, gained weight when burned, a finding fundamentally inconsistent with the idea that they were losing something during combustion. If phlogiston was being released, shouldn't the metals become lighter? Proponents of the theory made increasingly convoluted arguments to explain these anomalies. Some suggested that phlogiston had negative weight, or somehow created buoyancy, concepts that strained credibility and undermined the theory's initial elegance. The German chemist Andreas Markgraf had noted this weight increase as early as 1744, but his observation was often dismissed as experimental error. However, as more precise scales were developed in the mid-18th century, the weight gain became undeniable. These weight-related problems forced phlogiston theorists to adopt increasingly strained explanations that compromised the theory's simplicity. What had begun as an elegant explanation was becoming a patchwork of exceptions and special cases, a warning sign in any scientific theory. The downfall of phlogiston theory came primarily through the work of Antoine Lavoisier, often called the father of modern chemistry. Between 1772 and 1777, Lavoisier conducted meticulous experiments on combustion that would change chemistry forever. Using precision scales, he demonstrated conclusively that substances gain weight when burned because they combine with a component of air, which he named oxygen, from Greek words meaning acid former. Lavoisier's approach represented a methodological revolution as much as a theoretical one. Unlike many of his predecessors, he insisted on precise measurements and careful accounting of all materials involved in chemical reactions. His famous closed vessel experiments showed that the total weight of materials remained constant during combustion, establishing the principle of conservation of mass that would become fundamental to modern chemistry. In 1783, Lavoisier presented his oxygen theory of combustion to the French Academy of Sciences. His explanations were simpler and more consistent with experimental evidence than the increasingly complicated phlogiston theory. Combustion wasn't the release of a mysterious substance, it was a chemical combination with oxygen, a much more straightforward explanation that better matched the observable evidence. What made Lavoisier's approach so powerful was his systematic methodology. He didn't just offer a new theory, he created an entirely new chemical nomenclature that replaced the alchemical tradition's colorful but inconsistent naming systems. Terms like oil of vitriol gave way to sulfuric acid, creating a more logical system that reflected the actual composition of substances. This linguistic reform reinforced the conceptual revolution underway. By renaming substances according to their composition rather than their properties or origins, Lavoisier was embedding his new theoretical framework into the very language of chemistry. His 1789 publication, Elementary Treatise on Chemistry, delivered the final blow to phlogiston theory. It presented the first modern list of chemical elements and established the law of conservation of mass, fundamentally changing how scientists understood chemical reactions. This wasn't merely a new theory replacing an old one, it was a complete reconceptualization of what chemistry was and how it should be practiced. The overthrow of phlogiston theory wasn't merely a matter of better evidence, it involved complex social and institutional factors that reveal how science actually progresses. Lavoisier was not working in isolation, but was part of a new generation of French scientists connected to the state and industry. His position as a tax collector gave him the wealth to fund elaborate experiments and precision instruments that earlier chemists simply couldn't afford. The phlogiston debate also highlighted fascinating national differences in scientific practice. British chemists like Joseph Priestley and Henry Cavendish remained committed to phlogiston longer than their French counterparts. This partly reflected different philosophical traditions, British empiricism versus French rationalism, but also different institutional structures and social networks. Science was becoming increasingly professionalized, with formal academies and journals replacing informal networks of gentlemen scientists. These social factors were just as important as the experimental evidence in determining how quickly new ideas were accepted. Perhaps the most fascinating aspect of this scientific revolution is the story of Joseph Priestley. In 1774, Priestley had actually isolated oxygen, but he called it dephlogisticated air and interpreted his findings entirely within the phlogiston framework. When he met Lavoisier in Paris and described his experiments, Lavoisier immediately recognized their significance for his own developing oxygen theory. This episode highlights how the same empirical evidence could be interpreted radically differently depending on the theoretical framework a scientist was working within. Priestley had made the crucial discovery that would help overthrow phlogiston theory, yet he remained one of its most steadfast defenders until his death. This wasn't because Priestley was stubborn or unscientific, he was actually a brilliant experimenter. Rather, it shows how powerful existing paradigms can be in shaping how we interpret evidence. Priestley saw his discovery through the lens of the theory he already accepted, while Lavoisier, already skeptical of phlogiston, saw the same evidence as confirmation of something entirely new. The overthrow of phlogiston theory represents one of scientific history's most significant paradigm shifts, often called the chemical revolution. It illustrates how even widely accepted scientific theories can be overturned when they fail to explain new evidence. Perhaps most fascinating is how long phlogiston theory persisted despite mounting contradictions. The resistance to abandoning phlogiston demonstrates the powerful psychological and social forces that can maintain scientific paradigms despite contradictory evidence. Scientists had built entire careers around phlogiston theory. They had published papers, gained positions, and established reputations based on it. Abandoning the theory meant not just accepting new ideas, but potentially undermining their life's work. This wasn't just about evidence, it was about identity and community. The transition from phlogiston to oxygen theory represents not just a change in chemical understanding, but a fundamental shift in how science operates, moving from qualitative, philosophical explanations to quantitative, evidence-based theories that could be precisely tested and measured. The phlogiston story remains relevant today as a cautionary tale about scientific certainty. It reminds us that scientific theories are always provisional models, subject to revision or replacement when better explanations emerge. What makes the phlogiston story so valuable is that it wasn't simply a case of ignorance replaced by knowledge. Phlogiston theory was actually quite sophisticated and explained many observations well. Its failure teaches us that even theories that seem to explain the world comprehensively can ultimately be replaced. This historical episode teaches us that scientific progress isn't always linear or inevitable. It often involves false starts, blind alleys, and resistance to change. Yet the eventual triumph of oxygen theory demonstrates science's self-correcting nature and its capacity to discard even beloved theories when the evidence demands it. In this way, the story of phlogiston continues to illuminate not just the history of chemistry, but the nature of scientific knowledge itself. It shows us that science advances not just by accumulating facts, but by periodically reimagining the frameworks we use to understand those facts. The rise and fall of phlogiston theory represents far more than a scientific footnote. It marks the birth of modern chemistry and illustrates the messy human process of scientific revolution. For nearly a century, brilliant minds built an elegant theoretical framework that seemed to explain combustion, respiration, and metallurgy through a single unifying principle. Yet when faced with mounting contradictions, particularly the stubborn fact that metals gained weight when burned, the theory required increasingly convoluted explanations to survive. Lavoisier's oxygen theory triumphed not just because it was correct, but because it offered simplicity where phlogiston had become complex, precision where phlogiston remained vague, and a systematic methodology that transformed chemistry from a qualitative art to a quantitative science. The phlogiston story reminds us that science advances not through perfect theories, but through better ones, and that even our most cherished scientific explanations may someday be replaced by deeper understandings. In the end, phlogiston's greatest contribution to science may have been its failure, demonstrating that evidence must ultimately triumph over elegance, tradition, and authority. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.